So it is my pleasure to introduce Grace Miao, who's a PhD student at UCLA with Rick Dale and Matthew Lieberman. Grace has published a couple of very interesting papers, in particular one on formalizing models of coordination that are not just driven by alignment, which is super cool. And so I'm very happy to hear what she's going to present us today. And the word is yours.
Thank you. So thank you everyone for having me here. I'm really excited to be able to present my work with the center because your center is doing incredibly relevant work, and I'm just really excited to talk to all of you. Yeah. So I'm sure everyone in this room has had a first conversation with someone new, and you would leave the room feeling like it's awkward, or it's bland, or you really clicked with that person. Now, why do we click with some people but not others? That is a distinction that's very important to study because strangers who click with you could become a good friend or romantic partner. In fact, all relationships except for family bonds began as an interaction between strangers. And our close relationships are some of the most powerful sort of forces in our lives. Like the number good relationship is the number one predictor of health well-being. And the most powerful thing that shapes who we're close to in our lives is communication. Like it's the conversation that we have with people. Conversation is a primary medium in the process of people going from a stranger to an acquaintance to a friend and to a close friend. And I'm a communication interaction scholar because I really care about how conversations or social interactions in general shape our social connection in life. One of the things I'm going to focus on is this initial connection, the spark, the click that sometimes occur when people talk and sometimes don't occur when people talk for the first time. Because we're living in an unprecedented time of political polarization, of the rise of AI changing the global context of workplace, daily life, the way we communicate with one another, and also the way we communicate with AI. And there's also a loneliness epidemic coined by the US Surgeon General in 2023. Like, this is a time when connection is under major threat. And this is why it's so important, especially now, to study how people form meaningful connection, to eventually promote more meaningful connection in our society. But here's a challenge. In order to study how people form meaningful connections, we first need to know what it looks like in action, and we don't actually know that. So to approach this complex question, I asked two research questions. The content level is what happens when people feel connected through conversations. And on the method level is how do we study this process of conversation and connection formation. And once we answer these two questions, we'll be in a position to answer the big philosophical question about how people form meaningful connections. Now, to give a preview of the kind of tools I use and different kinds of conversations people will have in the lab, let me show you two videos. Don't worry about the funny hat on the head for now. I'll explain in detail later.
The neighboring countries of Norway. There's like Sweden and
Yeah.
Finland.
Oh my gosh.
And I think
IKEA
I really want to go to Denmark. I love IKEA. Goes hard. Zombie apocalypse?
No, okay.
IKEA.
For zombie apocalypse, no, it's Costco.
Thank you! Oh my
It's
god!
Costco.
Wait!
Like, it is flashing.
Yes, right? No, it is Costco.
No, but
because they have the giant doors, they have a ton of food, and they have weapons. They have weapons like knives and stuff like that.
Yeah,
but beds. People always.
Okay, so during this interpersonal communication process, we can see that not only do they align on a stance towards where they should be at zombie apocalypse, we also see it through their behaviors, like the hand gesture, body leaning towards one another, their voice, their pitch. Like all of these are communication practices that people systematically employ during a conversation. And in the next case, I'm going to show you what it's like when these communication practices are lacking.
I was always very paranoid because I always wanted to go to UCLA. Like it was my dream school. And my mom always told me if you ever get into like one fight, even in elementary school, and get suspended or something, because you'll get suspended, they won't let you into UCLA, they'll see it on your record. It worked really well because I had anger issues as a kid that I like learned to harness. So I never got into a single fight because of it. And now it's considered assault because I'm an adult. And so I'm like very sad I never took advantage of the opportunity.
Well, I believe some of us are starting to get uncomfortable. In fact, there are 14 seconds of silence here, to the point where the female participant would
Oh,
say,
I promise I'm not a violent person. Like,
Okay.
let me be clear, I'm not a violent person.
Okay.
Just,
You
yeah,
just love
the,
fighting.
the internal thoughts.
yeah, so the lack of reaction from the male participant actually make the female participant clarify herself that I promise I'm not a violent person after 14 seconds of silence. So, as you can see, there's an absence of communication practice, and then it will lead to some consequences in the interaction. So, in these conversations, a lot of things are happening at the same time. Like, there are these nonverbal communication practices, like the eye gaze, the hand gestures, um, like the yeah, facial expressions, the body leaning against each other. There's also like the verbal component of the conversation, like what did they actually say? How were those speeches delivered? In what sorts of interactional contexts? And in addition to all these, there are also these invisible processes underlying all of these behaviors in motion that we can't really measure just by transcript of video. And those are what's happening in the brain. And in the lab I come from, we have a lot of studies where people come in and talk to a person with whom they have lots of ideological disagreement. And even with all the things we know that they disagree about, they will have the most pleasant conversation. They just don't show the conflict during conversation. Yeah. But these are the places where neuroimaging is helpful. Like for the first time, I think we have a tool that actually can get us some part of the puzzle, revealing the neural signatures happening during these conversations. So overall, I not only want to study these modalities separately, but also want to figure out how to bring together these tools, new tools with existing tools, and then I will be getting to that part at the end of my talk. So overall, the question dealing with like what happens when people feel connected through conversation, I'll first talk about the neural signature of stranger bonding, and then some attempts to link the brain with verbal and nonverbal signals, and then theoretical modeling as simple dynamic abstraction that could also apply to real life eye tracking data. And then using DIMS dashboard to integrate data theory modality into one unified framework and some future directions. So, like rather than delving into every specific projects in great technical details, I'm actually doing like a sampler review of various projects I've been working on because like everything Interacting Mind Center does is incredibly relevant to my overall research program. I just really want to showcase like these are the things I'm working on, and if anyone has any interest in having further conversation, please definitely contact me. I would love to chat. So overall, for my experiment setup, I would invite two strangers to come into the lab and have a conversation with each other. So, and during these, yeah, and then so when they're having their brain being scanned, we also capture their like audio and their like visual behavior, and then these are all like strangers get to know you conversation over shallow, deep topics. Shallow topics are, for example, like what do you think about the weather today? How often do you come to UCLA campus? Deep topics are like what constitute a perfect day for you? Can you describe a time you cried in front of another person? What's a rather embarrassing moment of your life? So the deep topics are just much more personal than shallow topics. And on a behavioral level, we see that deep topics do promote stronger self-report connection, which aligns with the previous literature on this. And then when we divide people based on those who feel high or low connection, we also see that participants who felt more connected also reported experiencing greater conversational depth. Now, looking into the brain part, this is the neuroimaging tool we're working with, functional near-infrared spectroscopy. fNIRS. So fNIRS is this really cool, unique form of neuroimaging that fits really well with communication research or interaction research in general because it's portable, so that we can do neuroscience in real life in naturalistic setting. So, I think all the doctors around the world would use these pulse oximeter to measure the blood oxygen level on the fingers. So for fNIRS, it's kind of just like having 30 of these pulse oximeter on your head. So we can track the blood oxygenation fluctuation over time when you're actually doing an activity. So, And then in the social neuroscience literature, there's a term called the social brain, which are like what previous literature have found to be like brain regions that are relevant when people are doing social perception related tasks or processing. And then the one specifically relevant for us is the default mode network because it's responsible for sense making or like experiencing empathy, shared understanding, or navigating relationships and social norms. And then this is where the default mode network is located in the brain. So this top graph is the front of the brain, and then these are like the from the two left and right sides of the brain. And then the specific metric we're working with is called neurosynchrony. Um, like essentially, neurosynchrony is the idea that like let's say these red and blue are two people, and we're taking one specific point of these two people's brain, and we're tracking the activity over time. And then rather than treating these two signals as individual signals, we take correlation or wavelet coherence so that we're representing the two interacting people as one dyadic system to understand them on like a dyadic level compared with other dyads, how the neurosynchrony metric is working. So in the neurosynchrony literature, there are some literature that are relevant to like looking into how two people and seeing like how two people's brains are working when they're watching videos. Like for example, in this paper by Yuri Hassan's lab at Princeton, like they found that after participants watch cartoonish stories of shapes moving around and interacting while laying an MRI scanner, they were asked to recount the stories. And what they found is that those who had more neurosynchrony in the default mode network also described the stories in more similar ways, suggesting that they were interpreting them more similarly. And then in Carolyn Parkinson's lab in UCLA, they realized that if they have MBA students entering a new environment, watching some videos before they get to know each other, they could use that neurosynchrony for video watching to predict whether they form friendship 8 months later, after they have friends in the program. Now, what I'm trying to do is apply these findings in the neurosynchrony literature to see whether these results from the video watching experiments would apply to like conversation studies, like conversation is just much more complex compared to just watching videos together. So, building on behavioral results we had before, we found that there is a reliable difference across the two groups of high connection group and low connection group when we look into the default mode network neurosynchrony across the dyads. And then when we do regression analyses for that, we can find that the default mode neurosynchrony would be able to predict connection on a dyadic level. And then when we delve in to when we decompose this left graph a little bit to the people who are engaging in shallow, deep conversations, we can see that in the deep condition, the neurosynchrony like default mode network neurosynchrony has a much stronger effect in predicting the connection. And our like we have a lot of interpretations about this, some of which may be like when we're talking about whether how we feel about the weather today, like when we're building neurosynchrony around that, or talking about walking from point A to point B in the university campus, then like for people who are already students there, those are common knowledge for them. So they're thinking about the same thing, but that kind of neurosynchrony of thinking about predisposed knowledge may be different from like getting to know each other. Like if I were to tell you about an embarrassing moment of my life, and then you were to internalize that and form neurosynchrony with me, then those reflected in the much more personal, deep conversations is being showcased here, like in like a distinction. So overall, in the neurosynchrony finding, we see that the neurosynchrony in the default mode network is the key marker biologically for social connection. And a greater default mode synchrony during deep conversation predicts stronger self-report connection between partners. And also, for another set of analyses we've run, when we combine default mode synchrony with self-report depth of how deep do you think the conversation went, these two variables will allow machine learning models to classify high versus low connection dyads. So far, we have a preprint on bioRxiv, and the manuscript is under review if people want to check it out. But moving on to the next part of the talk, in addition to looking into just the brain by itself, I will also love to look into combining it with the verbal or nonverbal signal. So the first project here is talking about how we can link it with the verbal content. And this is an important question because interpersonal conversation is largely like a strategic plan and intentional enterprise. And there's actually like theoretical debate in the literature on whether a good conversation should be effortless or effortful. Like some literature is saying that satisfying social interaction are typically described as effortless, synchronous, and transcendent. But the message production literature also says that cognitive effort is crucial ingredient to accomplishment of communicative objectives. So, um, when we're trying to approach this question, we really think that combining the language and the brain should be able to approach this. And the concept we're building on, the metric to work with here is Claude Shannon's information theory, which tells us that entropy could be used as a measure of randomness. So measuring the mutual information between two utterances. Now, for example, here we have two utterances where the first participant says, I believe the temperature was in the 40s, so it's quite chilly but still manageable. There was snowfall once during Halloween. And then the other person asks, is it common for kids to go trick-or-treating? Then these utterances could be then put into Roberta to transform into word vectors, and then do cosine error for that. I'm not doing a lot of introduction on like Roberta or cosine error because I feel like the center here works a lot with these embeddings, so I'm just skipping that. But if anyone has any question about that, please ask during Q&A. Um, so once we have the cosine error, we can then feed that like into try to feed that into the Claude-Shannon entropy formula. And the way we calculate we do need to calculate a probability here because that's the component of the formula. And the way we do that is to use the equation here, like has a normal distribution with a mean of 0 to test the null hypothesis that two word vectors based on their cosine error are exactly the same. So like whether the last utterance and the next utterance are exactly the same. Then if we could reject that null hypothesis, then like we can just base on this formula and get a probability of that. And once we have a probability calculated based on that, we could plug it into this formula and calculate the entropy. And if you would like to have a detailed methodological explanation on that, it's published in a paper by my lab mate, Zach Rosen, and Professor Rick Dale in Behavioral Research Method. Now, we are trying to also find a measure in the like that we could use to quantify variation of brain signals per time step so that like we could like match with what is being captured by the convergence entropy in the linguistic the word embedding calculation. Then essentially like if the word embedding is being calculated to reflect on how much change or how much differences are there from the last utterance to the next utterance. We should also be able to find a metric to calculate how much does a person's brain pattern shift from one moment to the next. And then we landed on Allen variance for that. So have like this is like a simple illustration of what Allen variance is doing. So within person, if we look at Allen variance, like when it's low, you have like a stable signal. But with the same person, when there's a high fluctuating signal, Allen variances show as high. Now, applying that Allen variance statistical property to how similarly do two people's brains dynamic unfold across conversations, we found the literature by Abney et al. On like complexity matching using Allen variance. Then the way to understand that is that like between person, when people have high complexity matching, they're showing like very similar rhythm, like the top graph here. But then between person, when they have low complexity matching, they will have very drastically different rhythms. So yeah, so essentially we try to use the convergence entropy way of understanding large language model or like language embedding. Um, across utterance from like the last person to the next person, like how much change there are, and whether how much entropy or like mutual information there are, and then combine it with like this complexity matching of the Allen variance, which is reflecting on how similarly do these two people's brain dynamic unfold across conversation from the last utterance to the next utterance. Yeah. So when we link these two components together and doing them separately, we found that linguistic convergence is related to self-report conversational depth and bonding. Like as in, we could use how much convergence entropy in a dyad to predict how deep the conversation went and how strong a bond they're feeling after the conversation. Um, and then the linguistic convergence localizes to the deformal network and specifically the right temporal parietal juncture, which is a main region within the deformal network, which are the important parts of the findings from the study one. But then the interesting thing is we found a negative effect with this relationship, so that when language convergence occur, neural signals diverge. Yeah. And our interpretation is that achieving language convergence is effortful, so that brain resources are recruited to align with each other. And the way we think about this is like probably when we're listening to a lecture, like maybe the one I'm delivering right now. Um, the way I'm talking about a project, like even though the content has been difficult to formalize in my brain, but because I've been working on it for such a long time, when I'm delivering it, it would probably be very different from when you as an audience are trying to interpret what I'm talking about. And that interpretation is a very effortful process. Then let's say you ask a question that's highly relevant, and then using a lot of the words that I use during this conversation so that we achieve a high linguistic convergence at the end. Then like that means your brain is probably using a lot of effort to align with what I'm talking about, which the pattern of like delivering this information when it's already internalized in my brain versus like integrating it, like listening to it for the first time and trying to understand what is being spoken has like probably has like a very large difference in how much effort it requires. Yeah. So that's our current the like interpretation of the results, and then we're trying to write up this manuscript. Yeah, so this is work in progress, but love to discuss with anyone if you have any suggestions. Then the next project we'd like to talk about is like linking the brain with nonverbal signals. And this is work I'm doing with Joyce in Rick's lab and also Matt Lieberman. So overall, we just want to see that like whether it's possible to combine the brain and also nonverbal signals to predict how people feel about the conversation afterwards. And then the way we're trying to do this is using deep neural network to construct a multimodal analysis. So for facial data, essentially we just take the video we have and then we feed it into OpenFace, which is a machine learning algorithm that gives real-time activation to every piece of facial action units. So here we can see that like we have the inner brow raiser, outer brow raiser, and brow lowerer. And like that is by the Ekman literature on like facial action units to be like essentially what you're seeing here are like the different muscles across the human face that could like be controlling any possible facial expressions we could ever have. And then the first three here would control all of the possible eyebrow movements. So this machine learning tool essentially can give us real-time classification on like how much activation there and what is the intensity of the activation across different time points. And then, so once we have the brain data for every time point, and we also have the face data processed across time points, we're trying to think about how to combine them into one multimodal space. And then, so we use a deep neural network, specifically an autoencoder. And so autoencoders use numbers that human can't directly interpret as representation, with every layer of embedding containing more compressed information. So these embeddings could then be decoded back to the original data input. So essentially, the way we check that this process is running correctly is that the input and output look exactly the same. But then we will want to take the middle bottleneck layer that has the most compressed information and analyze that. So when we put the neural and the facial data in together, the bottleneck layer will contain multimodal information that merged the information between the brain and the face. Yeah. So we're hoping to do that and compare with what happens to the bottleneck layer with face-only data and also with neural-only data to see what are the differences, to just compare because there's not really much theories formed in the literature about how the human mind would process multimodal integration. Then we're just like, let's look into how machines do it and maybe we can get some inspiration. So this is largely like an exploratory project. Now, we derived several metrics to be able to look into individual dyads in these embedding layers. And the first one here is synchrony. So what you're seeing here are people. Like every dot here represents a person. The two black dots here represents two people in a conversation, like they're talking to each other. And then the gray dot is a comparison point in the same data set that is not somebody who is a part of this conversation. So what I'm showing, so what you're seeing here is the movement in the multimodal space over time. And then, so each circle here represents 5 seconds of the conversation data. Like, notice in the moving plot that the black dots are showing that the two people talking to each other in a synchronized fashion through this multimodal space. And neither of these two black dots look synchronized with the gray comparison dot from a different conversation. And the first time I saw this visualization, I thought it's pretty amazing that just by looking at the movement of these dots, it was quite obvious who was talking to whom among these three people. And then in addition to synchrony, we also have a metric that's distance. So as you can see here, while these two black dots are not very synchronized in their movements, they're quite close together and thus have low distance. So these are the two metrics we're using to try to understand how do multimodal neural-only and face-only signals differ from each other. Do they predict self-report experiences of conversations? And the way we answer that question, because we know that there are a lot of like black box processes going on with each individual iteration of deep neural network of any sorts. We just ran it 25 times for every single for every version, and then we got some and then we essentially for like every specific version here, we compared it against all of the outcome variables we have from like the self-report data, and then let's look into some of these results together. So in the what you're seeing here, for example, is the multimodal embedding layer. And then we're looking at the connection composite variable, the average score, and the different scores between the participants. So the bonding average here is, for example, how strong a bond do you feel with your partner right now? 1 is not at all, and 5 is very strong. And then the numbers you're seeing here is like across the 25 like simulations we've done, 25 iterations we've done with the multimodal embedding, like how many of them show a significant difference among the people who indicate like very high connection versus very low connection. So here, for example, let's talk about the bonding average. So like 25 out of 25 iterations for the people who feel very strongly bonded with one another. They have like significantly different patterns in this multimodal space compared to those who feel very low bonding with each other on like a dyadic level. So that bonding dyads behave differently in this multimodal layer compared to the non-bonding dyads. So other results we we see are reflecting on the future relationships, or like how willing are you to have a future interaction with your partner. And we also see some results on like the conversation attributes like enjoyment, how deep do you think it went, how awkward did you find a conversation to be. And then all of these we're seeing are on the distance metrics. And the most significant one in the similarity metrics is that how similar do you think you and your partner are? And that's within the multimodal level. Yeah, and when we look into only the neural, we see that the neural embedding differences are mainly reflected in the synchrony layer. Like, and it's predicting like how much difference and how easy was it for you to open up, and like how much do you enjoy the conversation with your partner on average, and how much do you like the conversation partner. And then when we look into the face only, we see that it's much more similar compared to the multimodal. So like the connection, bonding, and also the future relationships and the conversation attributes. Like even though like not these variables are not exactly 100% mapping onto each other, they look quite similar compared to the face only, compared to the neural only embedding analyses. So the takeaway here for linking the brain and the nonverbal signal is that autoencoders could be a powerful approach to generate truly multimodal data, where the embedding layer would be combining multiple modalities of data together, and then we can look into the joint contributions of these multiple different channels into um, how do people do multimodal processing. Um, and we see that like multimodal patterns reflect both the face and the neural data, but more strongly driven by facial features. And then synchrony features capture more rich nuance in the neural data, and distance capture clearer distinction in facial data. We do have a Coxside preprint about the method pipeline, like in terms of how to build, how we build this like a deep neural, like how we build this like sequence to sequence autoencoder. But then we're still working on like a manuscript to write like all these empirical findings that I just presented. So all of these are also work in progress. So please let me know if you have any questions. So far we've talked about the neural signatures and how we could combine the neural signature with the verbal and the nonverbal signals. And then for the next part, we're trying to have theoretical modeling of like how can we use simple dynamic abstraction to characterize all the possible like interactions between two people in a dyadic system. And the concept we're building on here is one that I'm sure that people in the room are very familiar with. This is synchrony and complementarity. And then it could be moving an object together, or it could also be like having turn-taking pattern when one listens, the other one is talking, complementarity pattern in speech. And when these patterns are violated, we can see miscommunication. So what we did in our conceptual model is that, let's say like Ricardo and I are talking to one another. There are four possible parameters that we could think of to characterize all of the possible things that could happen between us. It's how he influences me, how I influence him, how he influences himself, and how I influence myself. Like, so when we characterize all the possible interaction between us like that, we could technically just use four numbers in like this 2 by 2 matrix to characterize what all is like all the possible states. It could be like we're strangers not interacting at all. It could be like we're collaborating, trying to sing happy birthday song to reach perfect synchrony. It could also be like when I'm talking, he's trying to listen, or it could be like there's like a leader-follower relationship going on. So because of the time here, I'm not going to delve into all the details of this specific projects. But then yeah. Um Essentially, currently we have two papers on this. One paper is using pure like simulation. Yeah. And then this is essentially looking into like if we were to use three different states to characterize the four different parameters here to represent like there's an inactive states of somebody not participating at all, and then active states on like I'm actively talking right now, and in inhibitory states of like you're listening, you have a question, but you're trying to inhibit your question so that you could listen, like you could process my talk. That is an inhibitory state. Yeah. So when we do this like 2 by 2 matrix with like three possible values representing the states, we get like 81 unique combinations of the C matrix. Then we can use as like the initial states to do like a generative like agent-based simulation model um, of like what's going on. Like what would the time series look like? Like for example, when we're having a completely random state, we can see like the red and the blue lines are not really like interacting with each other much, and we have a very low R value. And then when they are perfectly aligned or synchronized, we have a R value of 0.64. And the perfect alignment example would be like singing Happy Birthday song together. Um, and then when there's a complementarity, it may look like the R value is not that high, but when we zoom into a specific chunk of it, we can see that it's the same curve mirroring along the x-axis. Um, and overall, like one of the findings we have is that um, in order to have like a um turn-taking pattern similar to like essentially like the negative correlation here in like a turn-taking pattern reflected by this simulation, we need to have at least one -1 parameter, like 99.8% of the time. At least one like -1 parameter needs to be there. Yeah. And then so this simulation part is already published on scientific reports. And then the next step of this project, we essentially trying to see whether we could use this like a dynamical system inspired model to predict real life performance metrics. Yeah, and then the way we did that is um, like we changed our like dynamical system model into the latent variable that's being predicted in the Bayesian formula. And that changed our model from a dynamical system model to a hidden Markov model in Bayesian. And then we were able to correspond it with like the psychological like with the psychological alignment, like calculated by CRQA and other metrics in visual search, used by like eye tracking data, used like performed by like stranger dyads also in the lab. Um, and then this is a preprint we have for this project, and then yeah, the it's under review right now. But the overall takeaway we have is that a highly simplified model could capture some basic properties of interpersonal dynamics. And in order for there to be a robust turn-taking pattern, at least one inhibition state must be included in the C matrix. And applying the model to human eye tracking data, we show that summary features of the inferred context matrix could capture expected task-based difference in the interpersonal dynamics. And we could predict the task accuracy in a psychologically reasonable way. And then we could show some correspondence with existing measures. Now, I'm sure after these three parts of the talk, which are highly computational, you may have more questions than answers in mind, which was exactly my personal point of view when I was doing all of these projects. Like I have to say, interpretation is very difficult. And then which is what triggered me to actually try to solve the problem of like it's like I find it very difficult to find a way to combine modalities together. And then so I was just like, if I can find funding and bring people from all around the world to like just discuss this process and like how we can combine things together, like like so that we could look into these like multimodal integrations together. And then this is what happened. I've hosted like a 3-day conference at UCLA, inviting experts from the Netherlands, from Canada, from various parts of the LA, like from of the US. And in talking with each other, we decided that the thing we wanted to do was to develop a tool, and we're calling it the DIMS dashboard. Now, DIMS not only stands for the name of this conference, but it's also abbreviation of dimension. Yeah. And then the DIMS dashboard really makes it easy to pull together all the things I've been talking about so far in my talk. And we're not doing it just for us, we're making this tool public. And let me show you a little bit of what that looks like and how we could use it. And okay. So what you're seeing here is a data dashboard. On the right, you can see the video recording of the interaction. Below that, the transcript of the conversation. On the left are all the extracted physiological signals from the same interaction, including the head synchrony, body synchrony, neurosynchrony from various social brain regions and networks covered by the fNIRS montage. Now, like what's presented here is not a traditional time series with raw data, but actually windowed neurosynchrony calculated over roughly a 5-second window, so that each point reflects the synchrony in the 5 seconds surrounding that moment in time. As a result, for the ups and downs here, you can see how the synchrony rises and fall, peaks and valleys, or sustained high and low levels over the course of the interaction. And then we could also see the same pattern for head movement, body movement, or if you want to use it to represent raw signals, that's also totally fine. To support exploration of long interaction, we added a rapid video preview feature. You can select a custom window size, let's say like 10 seconds, and then click on a specific moment in the time series, like the one highlighted there. Then a second window will pop up showing exactly that time that you have selected. So this makes it easy for researchers to visually inspect key moments in the corresponding video and allowing for more integrated interpretation, combining the quantitative pattern with qualitative observation in real time. Now, just for like a case study of what's happening here, it's like we're zooming into the neurosynchrony of a specific region within the deformal network. And then I noticed that there are 10 segments of sustained rises, where like during these 10 highlighted segments, we only see neurosynchrony going up, but not down. So I clicked on each of them and see what's going on in the video interaction. And I saw that 80% of the segments, people are showing high engagement in interaction. Like these high engagement could be verbal ones, like repeating each other's exact words. Definitely different, definitely different. It could also be performing overlapping speech during storytelling. Like, that sounds so cool. Oh my God, that's so early. Or they could be laughing together, or they could having like frequent head nods or similar rate of body movements during these 10 seconds. Now, from this, we could have like a qualitative finding that sharp rises in neurosynchrony may reflect moments of high mutual engagement. But we don't see this like quality-quantity loop stopping here. In fact, this qualitative finding could inspire another quantitative hypothesis. That is, we hypothesize that sharper increases in neurosynchrony will be associated with greater bodily synchrony across conversations. And then that is a hypothesis we could examine by running a regression analysis. So, and that's what we did. So what you're seeing here is the raw data, while the window synchrony data across the brain and also the head synchrony and the body synchrony. And then we isolated out the brain and just took the positive, we did like the first derivative calculation to just get the positive p-value, just to get the time points. So all the pink circles highlighted here are like the time points that we took from the data across like all of these various modalities in the top here. And then we ran a regression analysis and then we found significance. And this result is essentially saying that sharper rises in TPJ synchrony were associated with higher head synchrony. Now, this is just a case study, not a fully validated or generalized analysis, but I hope that this highlights the potential value of being able to seamlessly toggle between quantitative data and qualitative observation, using tools like this to surface meaningful moments and patterns that might otherwise be missed. If you want more info, and we have like a Coxside proceeding paper on this, and like here, this QR code will lead to my website, which has the details of the conference and what were the program like, and what are the associated reading. And then on the left here is the DIMS dashboard that's available for public clicking. Um, and then for the next step, we're doing some technical infrastructure. Like now we already have a client-side dashboard for users to visualize their own data, as long as you have Python installed and like have Visual Studio Code. And then it could also be like a GitHub shareable link if people feel like their video data is ready to be shared with the world. And then we're currently developing a point and click interface so that people who don't code at all could also use it, because there's a large body of scholars in like the conversation analysis and also gesture analysis world that we would love to be able to communicate with. And then we're also trying to incorporate more visualization tools that collaborator Wim is putting together very nicely in his website InVision Box. So like we're hoping that like the DIM Stasher will be able to incorporate some of these. Um, yeah, so that like there will be like a quality quantity cycle loop going on to decode the multimodality of human interaction, and then in like a very phenomenon driven approach, like because my work focusing on formation of meaningful connection, but it could totally apply to other important questions out there that other people are working on. And then if we could already combine the neural with some like head motions and everything, it could totally be possible to also combine in semantic, audio, and body movements. Yeah. So those are the existing work that I've already done. And just for like 2 minutes on like future direction, this is a project that I'm currently running data collection on. We're trying to see how human like form AI, human have conversation and form connection with the AI. So also like looking into the brain and into like the video recording of the content of the conversation, and also their facial signals and like the dynamic series and with like physiological trackers like wearable watches, heart rate, like all that, all the modalities we could think of. So the experiment is essentially we'll have every participant talk to three conversation partners. One is a human stranger, another one is a default AI assistant, which is like the for the current one will be the ChatGPT 5 one. That's the latest model. And then we also have a tuned AI partner that is a chatbot who really wants to be a UCLA student. Now, there's no deception involved, so that like this is like participants all know who they're talking to, and then we're just observing the conversation dynamics and also the connection they're forming. Now, this is a very important question because we see all these crazy news about people like breaking up with their real life boyfriends and trying to be exclusive with AI chatbots. We also see that a woman's marrying AI hologram these days, and like this man who married a hologram before, like actually is very heartbroken lately because the company that ran this specific chatbot went bankrupt, so he lost his wife. Yeah, so like, but in like all the things we see crazy in the news, like we also know people in our real life who would never do such things like that. Yeah. And then, in fact, we do see strong individual differences across participants when we just ran like a pilot session on just the voice chats. Like for some people, they're getting really emotional in just like a 10-minute conversation. It's like getting really, really sad, like actually tearing up about like how senior years flowing by, like they would love to be in UCLA for longer, like they really don't want university to end and such. And GPT was providing like guidance on like how to cope with like therapy, validating it, like what you should do and such. But in another participants, they kind of just wrapped up the conversation. And then the participants said, yeah, we still have a minute to talk. And then GPT says, we can just enjoy the last bit of our chat in companionable silence. And that's actually what they did. They just sat in silence for a minute until the time was up. Yeah, so yeah, so we spent like more than a year piloting this project because there are a lot of decision making involved with like trying to distinguish which are the technical issues to solve and which are the data pattern we're trying to capture. Like, I'm not going to go into details of these now, but I'm happy to talk to people about that if you're interested in. But overall, with this project, we're trying to answer how are human-human and human AI conversations similar and how are they different? And then what individual differences predict stronger feelings of connection with AI partner? And then how might the interaction with AI alter the way people connect with other humans? And then whether there's like an underlying neurosignature pattern that's like a biological marker of people connecting with anyone, anything else, or like just it's very different for connecting with AI and connecting with human. Now, thank you to all of the collaborators, professors that made all of these projects possible. I think we have a few minutes for Q&A.